Growing up, I always had this impulse inside of me to fear certain words, and this fear developed throughout the narratives that I would hear of the people around me, or simply by consuming any form of media. And one word precisely that frightens me up to this day is cancer. However, if science were to speak right now, we'd probably have to say that the stigma surrounding this word is starting to collapse, as technology and progress are making it curable. And that's a reality that I've been fed my whole life, and it's probably also the case for most of you. However, if we take a look at the statistics, we'll actually find something much different. So when talking about the deadliest cancers, we'll often refer to three specific ones that all present a common tendency to remain asymptomatic in their early stages. And by that, I am talking about lung, pancreatic, and ovarian cancer. And so if we take a look at this figure from the National Cancer Institute detailing the 5-year survival rate evolution of 17 different cancers from 1977 to 2013, we'll actually notice that not only do these three cancers present a very low survival rate, but also no significant improvement in their ways to fight it, in comparison to all of the other cancers combined. And so now, what other common factor could they possibly share on top of these two? Well, surprisingly, they also present a very low funding to lethality score, which is a metric used to determine how much funding is allocated to each disease in relation to its mortality. And so from this figure, we can simply conclude that lung, pancreatic, and ovarian cancer are simply underfunded. But to understand why they're underfunded, we need to understand the fundamentals behind cancer funding. And as we just saw, the burden carried by disease is often not enough to attract funding. Instead, some sources will claim that it's all about the narrative. If a disease does not encompass a social movement or passionate advocates, it will automatically be underfunded. And to illustrate that, we can take an example on breast cancer, who's strongly associated with women's rights, one of the most powerful movements of our modern era. And on the other hand, you will have lung cancer, whose main victims are smokers. And therefore, from this simple observation, our human nature will tend to favor a hardworking woman over someone who could have easily prevented their cancer. And sadly, this situation often leads to less progress and less funding being made, which leads in the end to a survival rate for stage 3 lung cancer to be at 4%, against 72% for breast cancer. But I'd like to clarify that with these 8 minutes of your attention, my purpose is not to divert funds away from cancer that are already well supported, but rather to say that with the fewer funds available, we might still be able to make some impressive progress in comparison to other well-funded cancer. And I believe that all of this could be made possible with artificial intelligence. And again, this might appear as deja vu since AI has been known to help cancer research for years. If we just take example of a study done in 2020 by Swedish researchers who found out that AI algorithms could detect 20% more cases than a group of radiologists. Or another one done in 2024 by Oxford universities who found out that AI algorithms could detect 2 types of prostate cancers. But again, I'd like to clarify that my point is not to reiterate what was accomplished in the past, but rather to highlight a different facet of this technology that could possibly cure the deadliest diseases with affordable cost. But before relating AI to these 3 cancers, I believe that it's important to ask ourselves, what makes these 3 cancers so deadly? And so, ovarian, pancreatic, and lung cancer will all show the common tendency of remaining asymptomatic in their early stages. And with the absence of any proper screening test, doctors will often have to rely on the identification of symptoms to make a diagnosis. And unfortunately, these diagnoses are often confused for colds or headaches in the case of lung cancer, or simply for menopause in the case of ovarian cancers. And by the time noticeable symptoms actually appear, the cancer will have already spread in a way that can't be cured. And so from that, we can understand that an early detection of cancer is probably the solution. But then how could we, or should I say, how could a machine detect early on a cancer not even perceivable by the human eye? Well, the same way that we learn to associate words with images, a machine will be trained to recognize patterns throughout large amounts of data in order to create for itself a model as to what, for example, a normal X-ray might look like versus what a cancerous X-ray might look like. And the more data is fed to the algorithm, the more accurate will the machine become until reaching a level of perfection. So far, I've stated a few statistics regarding cancer, as well as potential solutions to cure it. but I haven't explained fundamentally what is cancer. So cancer always begins at the cells level, when alteration in a cell's DNA leads to uncontrolled cell division as well as abnormal growth. And another important fact to know is that DNA are responsible for encoding proteins that will overlook the entire cycle of a cell, including its growth, division, and repair. Therefore, if these said proteins are damaged, we will observe a cell proliferation leading to the formation of a tumor. And more often than not, these tumors will metastasize, or in more simpler terms, spread to surrounding tissues. And from what I just explained, cancer kind of appears as a pretty simple disease, but there's only two factors that hinder the process leading to the cure. The first one lies in the heterogeneity of mutations, meaning that within a single type of cancer, we might observe different mutations from a patient to another. Therefore, it's pretty hard for scientists to conceive of a universal treatment. Then, on the other hand, we have to take into account the fact that mutations will accumulate over time, and that not all of them play an active role in cancer. In fact, we can separate mutations into two different categories. We're going to have the driving ones that will play an active role in spreading the cancer, and we're going to have the passenger ones, the one that will not spread the cancer to any surrounding tissues. And to be able to find a cure, we need to identify the driving ones, which can be complex in an area containing an unnecessary amount of passenger mutations. And so all of the complexities that I just mentioned are usually dealt with technologies like X-ray crystallography that will be able to model DNA and proteins. However, the problem with these technologies is that they're often expensive and quite ineffective, making the entire process last dozens of years, if not more. And so for that, I propose to use AlphaFold, a technology that was actually designed by Google DeepMind and actually won the Chemistry Nobel Prize just this year. And the way that it's going to work is that it's going to follow the exact same structure of an AI algorithm that I explained previously. And by that, I mean is that it's going to learn the structure of proteins coming from millions of other organisms, and it's going to build a certain understanding from that in order to accurately predict the structure of mutated proteins by simply looking at their amino acid sequence. And what makes AlphaFold so special lies in its ability to accurately predict the structure of these mutated proteins, where scientists can now actually spot the weak points of that proteins to design drugs that will neutralize the function played by that protein in cancer. And I believe that this technology could be beneficial on the basis of two aspects for the three cancers that I mentioned previously. The first one lies in the fact that by modeling proteins, scientists can now look for them in blood tests at an early stage in cancer. And on the other hand, the very fast and reliable nature of AlphaFold makes the entire research process go by much faster, therefore require less funding. So far I've talked about cancer, AI, proteins, and DNA, which are probably concepts that you're not familiar with and will probably forget within the next hour. But I'm not asking you to remember what I just said. In fact, I just want you to remember this. AI is often very despised due to its lack of human qualities. But I believe that what makes this technology such a controversial one might be the only aspect justifying its relevance in the context of underfunded cancers. And by that, I mean that when faced with death, technology does not favor any diseases over another, regardless of how popular a cancer might be. Thanks.